today we're going to be looking at the periodic table. So I'm going to go over the basics first. On the left side of the periodic table, you have your metals. On the right side, you have your non-metals. And the periodic table is arranged in groups and rows. A group is basically the columns of the periodic table. And the group number tells you the number of electrons in the outer shell. So an element in group 5 will have 5 electrons in the outer shell. An element in group 2 will have 2 electrons in the outer shell. So you've got group 1, 2, 3, 4, 5, 6, 7, and 0. Group 0 can also be called group 8. It's also arranged in rows. And the row number, rows are what we call the periods of the periodic table. And the period or row number is equal to the number of shells. So you've got like helium there and hydrogen there. That'll be the first row. And hydrogen and helium, they would have only one shell or one orbital. And then you've got the second row, then the third, then the fourth, and blah 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 blah. So they correspond to the number of shells. And the periodic table is also arranged in increasing atomic number. Not an increasing mass number, because if it was an increasing mass number, then argon and potassium would be swapped over, because argon has a higher mass number than potassium. So it's arranged in increasing atomic number. Now, how do you know the difference between atomic number and mass number? I'm going to go over that next. Okay, so here we have the example of carbon with something that's 12 and something that's 6. You may also see carbon written as this. So, knowing the number on the top and the number on the bottom does not tell you the mass or atomic number. It's not top and bottom that differentiates it. But the mass number is going to be the bigger number. So here the bigger number is 12. Whether it's on the top or on the bottom, it's the bigger number. That will be the mass number. And the smaller number will be the atomic number. Now, what does atomic number and mass number actually mean? The atomic number is the number of protons in the element, and the mass number is the number of protons and the neutrons in the element. So that's why you would expect the mass number to always be bigger than the atomic number. They might give you a question like, say carbon has a mass number of 12 and has 6 neutrons. What is the atomic number of carbon? Well, atomic number is the number of protons, and mass number is the number of protons and neutrons. You've got 6 neutrons plus something that's going to give you to 12. So 6 neutrons and a number of protons is going to give you the mass number of 12. 6 plus something gives you 12, and that's 6 plus 6. So we've got 6 protons, therefore the atomic number is 6. So you have some points on Newland's version of the periodic table and Mendeley's version of the periodic table, which is now our modern version. Newland arranged his periodic table in order of reactivity, and there's a pattern of reactivity in every 8 elements, and this layout was thus called the law of octaves. And he arranged it in columns in order of their atomic weight. But the pattern did not work for all the elements. I mean, you had some blocks that had 2 elements in them, and you had metals in a column with non-metals. And now with Mendeleev, he arranged it also in order of reactivity, arranged it in based on the reactivity of the elements, but this time increasing atomic number. And the main thing is he actually left gaps for unknown elements that were not yet discovered. And he predicted the properties of these undiscovered elements based on their position in the periodic table. Predicted properties. And when the elements were actually discovered, his predictions were true, and the elements fit the pattern. And that is why his version of the periodic table is now accepted as, well, our version of the periodic table now, the modern version made by Mendeleev. Next. Okay, so now we're going to talk about the alkali metals. I've got 3 examples: lithium, sodium, and potassium. Lithium being at the top of group 1, and sodium the second, potassium the third. And you can see that as you go down the group, the number of shells increases because the row number, because they're on a higher row number, or lower. Like this is in row 2, this is in row 3, this is in row 4. Corresponding to the number of shells they have. But the one thing they do have in common from their electronic structure is the fact that they have 1 electron in the outer shell, because they're all group 1. Group 1, 1 electron in the outer shell. And group 1 metals are extremely reactive, and they react vigorously with water. They react vigorously with water. And they all react with water to produce a metal hydroxide and hydrogen. So the group 1 metal plus the water gives you a metal hydroxide, and this metal hydroxide is an alkali, and also hydrogen is produced. And you can tell that from the fizzing when they react with water. When they react with water, there's fizzing, and that's the hydrogen gas that's being produced. And some of them react more vigorously than others. Okay, lithium, less vigorously, but as you go down the group, their reactivity increases. I'll explain this in terms of the electronic structure later. Potassium, when it reacts with water, it produces a lilac flame. And that is the hydrogen burning. And so, with these metals, there's an extreme exothermic reaction. Exothermic reaction. When they react with water, produce lots of heat. And some of them even form bonds, and they melt. Sodium and potassium, they melt when they react with water, but lithium does not. One more thing, they actually float on the water, because group 1 metals, they are very soft and relatively low density. Let's talk about their density and hardness. I just talked about that right now. The group 1 metals have low density, but as you go down the group, the density actually increases. Hardness, they're all very soft. They're soft metals. And as you go down the group, they actually become softer. Let's talk about their boiling and melting points. Again, relatively low. And as you go down the group, the boiling point and melting points actually decrease. And as I said, the metals are very reactive. They have to be stored in oil. Why? What does the oil do? Well, these metals are so reactive, they react with air. And so, storing them in oil prevents them from, so they are prevented from reacting with air and other gases, as well as water itself. So cannot react with water, cannot react with air when they are stored in oil. Now let's move on to the explanation of the reactivity of these metals in terms of their electronic structure. Okay, so we have the electronic structure of lithium and the electronic structure of potassium, both of which are group 1 alkali metals. And as you go down the group, the reactivity increases. And the reactivity of these metals is based on how easily or how difficult it is to lose the outer electron. Because remember, these are stable elements, but when they bond, like ionic bonding, when they bond ionically, they lose one electron. And obviously, therefore gain a positive charge, because there's now more protons than electrons. If they lose one electron, there's going to be one more proton than there is electrons, so the charge is going to be +1. I'm not going to go into too much detail on that because those aren't really the big marking points. So why does the reactivity increase as you go down group 1? Well, as you can see, the nucleus is obviously here, right? And as you go down the group, the outer electron is further away from the nucleus. So what? Well, what are these X's? What these X's represent? They represent electrons. And electrons have what charge? Electrons are negatively charged. And what do we know about positive and negative charges and electrostatic forces of attraction and repulsion? Imagine a magnet, but electrostatic forces of attraction. You've got negative here, negative here. So like forces will repel. If you've got a negative and a negative, they will repel. A positive and a positive, they will repel. If you've got a positive and a negative, they will attract. It's like a magnet with north and south. And so, because the outer electron is further from the nucleus, why is it further from the nucleus? Because you've got more inner shells. And because you have more inner shells, you have more inner electrons, which are also negative. And so, there's more repulsion force pushing this electron away. Remember, the reactivity of these metals is based on how easily they lose that electron. If there's a bigger force pushing the electron away, they're going to lose it more easily, making it more reactive. And this is called shielding, or you could call it repulsion. So all these electrons are negative. This electron is also negative. More electrons, more inner shells, more repulsion, pushing that outer electron away. And so therefore, the outer electron is more easily lost. And those are your 3 basic marking points. Now let's move on to the halogens or halogens, whatever you call them. Okay, so now we're going to talk about the halogens. Here are your group 7 halogens: fluorine, chlorine, bromine, iodine, and astatine. But the main ones you need to know are these 3. Now all group 7 halogens are diatomic. What does that mean? 2 atoms. F2Cl2, Br2. They're all diatomic. And their melting and boiling points are extremely low until you get to iodine, which is like a solid at room temperature. This is a gas at room temperature: gas, liquid, solid, and yeah. So their melting and boiling points increase as you go down the group. Bonding with metals, they form ionic bonds. And so, what is their ionic charges? Well, it's minus. You've got fluorine. Actually, you don't need to know them because it's on your data sheet. Cl minus, Br minus, minus, minus. You've got the data sheet, so you don't need to memorize them, but you should know that they become negatively charged when they form an ionic bond with metals. But with other non-metals, they form covalent bonds with non-metals. Reactivity. The reactivity of these elements, unlike group 1, decreases as you go down the group. And I will explain that next. So a displacement, the more reactive element will displace the other. That is your general rule. Here you've got potassium chloride, here's a halogen, and fluorine gives you potassium fluoride and chlorine. What has happened? Fluorine has displaced the chlorine in potassium chloride. So you have your potassium chloride. The fluorine has replaced the chlorine, giving you chlorine on its own. So fluorine has displaced chlorine. Why? Because it's more reactive. The higher in the group, the more reactive. As you go down, reactivity decreases. And now I'm gonna explain why this is the trend in reactivity in terms of electronic structure. Okay, so we have two examples, fluorine and chlorine. Now one other thing group 7 have in common is they have 7 electrons in the outer shell, missing 1 electron. And so if they're going to ionically bond, they will have to gain 1 electron. And that is why when the ions are negative, because you have more electrons than protons if you gain an electron. And the reactivity is basically based on how easily the electron is gained. For group 1, it was how easy the electron is lost. Here it's how easy the electron is gained. So basically the same points, but the opposite. The distance. If the electron is going to be gained, if the element has less shells, the electron is going to be closer to the nucleus. It can get closer to the nucleus. Remember, the nucleus has neutrons, which have 0 charge, and protons, which have a positive charge. An electron is a negative charge. So the positive charge of the nucleus, not the atom, will attract this electron. And the less shells the atom has, the easier it is for the electron to be gained, because it can get closer to the nucleus. But as you go down the group, more shells, so it's harder for the electron to get close to the nucleus. So then electron can get close to nucleus. Inner shells, like what we talked about before, repulsion. There is more repulsion as you go down the group because there's more inner shells, more shielding. In this case, it's a bad thing because you want to gain this electron, not push it away like in group 1. And so there's more repulsion of the electrons with that electron. And so it's harder to gain. So the repulsion or shielding. Because remember, the electrons are negatively charged. More inner shells as you go down the group, more electrons in the inner shells. So more stronger electrostatic repulsion force keeping this electron away. You don't want that, which is why it's harder to gain the electron as you go down the group. And the third marking point, as I just said, and I kept saying, electron is harder to gain as you go down the group. So as you go down the group, the electron, it's harder for the electron to get close to the nucleus, and there's more repulsion as you go down the group, and so the electron is harder to gain, and that is the explanation of the reactivity decreasing as you go down the group for group 7. Remember, with group 1, same marking points, but the exact opposite, because it's based on how easy the electron is lost. Here, it's based on how easy the electron is gained. And those are your 3 marking points. That's what I'm going to go over today. So, bye!